Hello, my name is Paul McKenney. I'll be talking to you about the price of fast and robust concurrent software here at Performance Summit 5. Alright. So, overview of what we'll be talking about, but I'm not going to dwell on that. First though, I want to talk about the goal. And this was motivated by seeing the panel session from last year. And there was some people that were calling for performance to be cool again. And I can understand that. We can all want to be appreciated, and being cool is definitely one way to be appreciated. However, keep in mind that you need to be careful what you wish for. The reason things are cool is because they're the big blocking thing that has to be gotten out of the way to make progress, and right now that's mostly security. There's some advantages to not being cool. One advantage is that you don't have people breathing down your neck when you're trying to do things. You're able to do things in a little bit more organized way. And you can just get things done and not have to worry about being yelled at quite as much. So we should be careful what we wish for. Being cool is great, but yeah, being uncool has its advantages. With that, let's take a look at semantics. If we're going to have robust software, we need to have solid semantics, so let's start here. Well, I'm going to use Linux kernel RCU for most of my examples. I'm not going to go through in detail what it is. There'll be some URLs and so on at the end of the deck that talk about them, and it'll be available as well. But the key point is that RCU has trivial formal semantics. RCU grace periods wait for all pre-existing readers. Readers are delimited by RCU read lock and RCU read unlock. As you can see, those do nothing. You've got an as in there. It has no code, quote, quote, right there. All it does with the memory directive is to prevent the compiler from doing code motion optimizations. RCU dereference is another piece in there. It picks up a pointer. It uses a volatile cast to pick it up. Nothing going on there either. RCU assign pointer is a store release. What could be simpler? And the thing that does the waiting just schedules itself on each CPU in turn. This is code that would run, in fact does run as part of the test suite in the Linux kernel today. And on the read side, this is production quality. The update side could use some help, at least the synchronized RCU part. And this is trivial. We got stuff that just does loads and stores and does nothing. Let's face it, we should be able to formally verify the stuffings out of this. Unfortunately, this being the real world, there are limitations. I mean, here's your synchronization mechanism. Elegant, wonderful, little puppy dog. Soft, it's warm, it's cuddly. What's not to like? Again, this is the real world. The real world has complications. This is how many fit in the slide. It's not a full list. Obviously, I'm not going to go through all of these. I'm going to pick on one of them. And that is, if you're a synchronization mechanism and there's an idle CPU and you make it wake up, you're going to have some low-power embedded people really upset at you, especially if the device is battery powered. In fact, they're going to be so upset, it's not going to be enough for them to flame you on Linux kernel mailing list. Instead, in one case, a rather memorable case, they called me on the phone and they yelled at me. I'm not making this up, this really happened. So this may be difficult to represent in all the formal semantics frameworks that it is today, but it's clearly extremely important. RCU must avoid disturbing idle CPUs whenever possible. Now, one complication, CPUs can switch back and forth between idle and not really quickly. In fact, if you have an idle CPU and it takes an interrupt for whatever reason, it's not idle anymore, and RCU must pay attention to it. Okay, well that's not a big deal. Just count the interrupt nesting level, right? Get an interrupt, count up. You return for interrupt, count down. There's special function calls in the Linux kernel that record both the up and the down. No problem. Well, not anymore, but when I was doing this work, one of the problems was that the Linux kernel could interrupt and never return. This was used intentionally. It was part of a way of communicating with user space. So if you counted, what would happen is you'd increment and never decrement. And then you'd never reach zero, and you would never avoid disturbing the CPU, and you'd have embedded people upset at you. So this was just one of the issues that showed up with low power work. I had to rewrite the energy efficiency portions of RCU something like 8 or 9 times over a period of some years before I got something that measurably saved real electricity on real hardware. So the thing is, the puppy dog doesn't cut it here. that puppy dog scheduled on all the online CPUs would interrupt the idle CPUs all the time. Okay, and that's not acceptable. We can't have the puppy dog for Linux kernel RCU. Instead, we need something like this, something that can defend itself. We need a polar bear, full-sized one. And something like that might actually survive. And the key point here is that semantics are but the tip of the iceberg. I mean, the mathematical things we can express in formal things are just one aspect of the requirements Linux kernel RCU and real-world software must meet. Of course, semantics applies to all software. What's the big deal for concurrency? Then the answer is that concurrent software is less mature and the semantics are less well understood. It's developing more quickly, the semantics are changing more quickly. So it's more of a challenge for concurrent software than it is for sequential software. But it's not the only challenge. Let's look at this from a software engineering viewpoint. Well, software engineering allows you to predict things like bugs and time and development time and so on. And if you apply that to RCU just counting the bugs, we have RCU containing about 17,000 lines of code. We have, now on a good day, I might be able to keep my bug rate down to 1 to 3 bugs per 1,000 lines of code. But to do the multiplication, you end up with somewhere between 18 and 53 bugs. Well, we can do better. The best case I've seen was 0.04 bugs per 1,000 lines of code. That's about 1 bug per 25,000 lines of code. But they had to kill themselves to get that. It was a safety critical thing, and they had really severely restricted software development requirements for good reason. And they still had more than 0 bugs. Another way of looking at it, in case that isn't depressing enough, is that RCU has to change fairly quickly, and thus the median age of a line of RCU code is less than 4 years. Old stuff often tends to be less reliable than new stuff. I'm a case in point, I suppose, but with code, young code tends to be buggier than old code. Therefore, we got more bugs here. They're just more bugs. Now, one way to deal with this, the classic way to deal with this, is just to get it right and never change it. This is the old school way. In fact, there was a case about 20 years ago that involved a data center, really small one, 1990 style data center, that was not meeting its availability SLA. It was missing it by quite a bit. So we sent a team in there, they took a look, and they made 2 changes. Once they made those 2 changes, no problem, met the SLA all the time. The 2 changes were to require management sign-off on all changes, no matter how trivial. And the second change was to install a lock on the machine room door and keep it locked. Well, that doesn't really fit very well with our current software development, especially my employer. Concurrent integration, concurrent deployment changes all the time. And so stasis maybe was okay in the 90s, it certainly isn't okay here in the 2020s. And it gets worse. There's something called installed base. I'm going to use my own history with installed base as an example. My first professional computer program was pro bono for the National Honor Society, a computer dating program from a high school. It had 1 user. So if I had a million-year bug in there somewhere, we have a bug happening once in a million years. We did have a bug. It was a data entry bug. We miscoded a senior girl's preferences as for freshmen rather than seniors. So she got assigned 4 freshman boys, and she was extremely unhappy. That was my first education in software customer satisfaction, or lack thereof. As time went on, I did more projects. And the thing is, at that time, everything can happen will, eventually. Maybe in geologic time, but still, there was a bug. In the early 80s, I did contract work, maybe a few tens of installments. The million-year bug happens once per 10 millennia. No big deal. In the early 90s, I was working for Sequent. We had maybe 6,000 installed base, 6,000 systems out there. Our million-year bug happened once per century, so we could, if we didn't have too many of them, ignore it, maybe. 2005, I don't know how many Linux kernel instances were running, but let's just say 10 million. In that case, that million-year bug's happening once a month, which is getting a little more concerning. 2015, the smartphones and Android smartphones were definitely there. They were full bore. There were at least 2 billion of them. And that turns into several instances per day. Million years, billion systems, there you are. In 2017, a guy who worked for ARM told me that there were at least 20 billion, that's 20 and billion with a B, instances of the Linux kernel out there, several times per hour. That's pretty vicious. But it might get worse. There's a thing called Internet of Things, IoT. Let's suppose that Linux gets 10% market share. Maybe it gets more, maybe it gets less, who knows, but that's easily $1 trillion. And I'm sorry, you don't want to know. But my concern is that maybe Murphy's transition from a nice guy back in 1975 to a 2025 homicidal maniac. Because, I don't know about you, but I'd feel really, really bad if my software ended up killing somebody. But here we are. And you got 20 billion systems with Test RCU? I doubt it. I don't. But fortunately, my current employer is very generous with systems for testing. And I've learned a lot of nasty tricks over the past 30 years on how to make a small number of systems cover the cases of a large number of systems. Not perfect, but it's still way better than nothing. In fact, back when they're using smartphones as phones, they don't anymore, but when they were, I could claim that 1 week's worth of testing on a 16 CPU system exercised RCU as well as 1 billion smartphones did for a full year. So I could do reasonable testing. I've had to get much more clever and creative since then. Okay, well, fortunately, RCU is way down on the software stack, and there was a time when I thought I was so far down on the software stack, I'm not just in the Linux kernel, I'm in the bottom of the Linux kernel. I mean, there's lots of stuff above me, and so we got some black hat in some cloud somewhere trying to attack me. Well, there's a lot of stuff in the way. However, I got my attitude adjusted a few years ago with something called rowhammer. Rowhammer attacks the dynamic RAM. Okay, what's rowhammer? Well, the thing is, you can have memory chips, those are the blue boxes, and they have bits, the green boxes. And these blue boxes might be in different protection domains. It might be in different pages. It might be owned by different users. You know, it might be that there's hardware preventing user A from flipping the bits on user B's side, except some researchers demonstrated, using real hardware, they really did this, that manipulating one bit could, via electromagnetic interference, change the other bit, even though we had memory protection there. And we don't get to abstract our way out of this. Plus, there's things like side channels, Spectrum Meltdown, that have shown up since then. So life is hard. Furthermore, in RCU's case, this is not just a theoretical possibility. A few years ago, well, it was actually a misuse of RCU. I could claim that I wasn't really to blame, but Linus had a different view on it. He asked me to fix the RCU so it's more usable, to repair a usability bug. Rightly so, and I did do that work. But there really was an RCU bug that was exploitable. And if you want to look into it, there you are. So, software stack depth is no defense. RCU is vulnerable, and I have to put up with the fact that there are malicious actors who may be attacking my code. In fact, I should assume that there are some. Alright, well, let's take a look at natural selection. Of course, if we're going to discuss natural selection, we really have to have a photo of the great man, and here he is. And maybe this can help overcome all these other problems we've talked about. We use natural selection. I mean, after all, natural selection in Darwin's time dealt with living beings, and it still does. But we've since learned that living beings have this stuff called DNA, which has amino acids that are grouped 4 amino acids per codon, and these things are kind of like a computer program. They tell the cells what to do, what proteins to release, and what other things to do, how to grow, and so on. And so what this means is natural selection, even in the wild, even in Charles Darwin's day, unknown to him, applies to software. So if that's true, it should apply to computer software, right? I mean, okay, we got software, which is randomly generated, and okay, you may take exception to that, but I've been doing this for 40 years. I've been watching a lot of people doing it. I'm watching myself do it. If you don't like it, too bad. Live with it. That's the way it is. But we have validation. We can apply natural selection, and if we got a bug, we'll get a test failure, we'll make a fix, and if we're lucky, we'll have fewer bugs after we do the fix than before. In fact, usually you decrease by a factor of maybe 7 to 10 to 14, somewhere around there. Most fixes do not inject bugs. So if you keep going around that loop, eventually you'll have robust software coming out the bottom. So here we are, we've got all these problems we've gone through, we use natural selection to fix them. Except, accept. Many years ago, early days for Linux kernel RCU, I got a bug report from a guy I'd never heard of in Russia. He was running RCU, running Linux kernel. He was doing something like 200 kernel builds concurrently on a 2 CPU system, just massively overloading it, and get a failure about once a week, and it was clearly RCU's fault. So I asked him for his .config file so I could work out why my tests weren't finding the problem. I mean, I should be able to run what he runs and make the problem happen and look at it, right? But silence, no .config file. Well, okay, fine. And a few months later, a guy from Australia reported that if he ran a really heavy test load, he had the thing roll over a few days as well. So I asked him for his .config file. Silence. Am I being trolled or what? I don't know. But a few weeks later, the guy from Australia comes back and says, yeah, I spent a couple weeks developing these massive trace facilities to find this deep, dark bug within the guts of RCU, and it turned out to be an initialization problem. At which point the guy from Russia replied with a single word email. Bastard. And suddenly I had great insight as to why I didn't get any .config files. The problem was that Linux kernel had incorporated hibernation and suspension. Suspend and hibernation resume. And to make that work, you have to enable CPU hot plug. So that meant my tests were no longer running without CPU hot plug, even the ones that I meant to run without CPU hot plug. And that meant a bug slipped in that affected only CPU hot plug. My tests didn't find it, and theirs did. So what the problem is that bugs are software. That means that bugs are subject to natural selection, so we don't get robust software at the bottom of this loop. We get software and bugs adapted to the validation. And this, of course, is why test suites tend to degrade over time. They stop finding bugs because the bugs they would find have been found, and the remaining ones have adapted. So we need something like this. It's simplified, you need a lot more, but you get bug reports in the field, you improve your validation. In fact, what you need to do, the thing is, natural selection is kind of a euphemism. It's natural selection. Mother Nature does natural selection by killing things. And the things left over are things not killed. So if your tests aren't killing your software, that is, if your tests aren't failing, then your tests aren't helping improve your software. What that means is at any point in time, you have a first-class bug against either your software or your test suite. There's either a bug in your software. In fact, software engineering, we know there's bugs in your software. But if your test suite passes, your test suite is buggy because it failed to find the bugs we know are there. Okay? So if you really want to get robust software, you need to take passing tests as seriously as you take failing tests. Both of them indicate bugs. So what's the price of robust concurrent software? We've gone through these different aspects. We've seen the semantics are only partial. They don't cover a lot of things. They're functions of time. And that means even if you did have a perfect specification, a few weeks later, it's going to be wrong because workloads changed, hardware changed, firmware changed, something changed. Software engineering, we know there are bugs in there somewhere. No matter how many you fix, there's still more, and we need to be chasing them. It's much, much more comfortable to fix a bug in the comfort of your own office than it is to have somebody report it to you. Installed base, well, success is the enemy of robustness. You have something that works great for your 10 friends, suddenly you have 1,000 people or even 1 million people using it, and all of a sudden bug reports are flowing in. So as your installed base increases, as a matter of self-defense, improve your validation. Software stack has no defense. Black hats are going to go deeper than you do. There's a lot of them. They're very smart. They're very motivated. Natural selection can help, but only if you really accept, hammered into your soul, that successful testing isn't a success. It's a failure of the test suite. So the price of robust software is eternal bugs and eternal validation development. Since things are changing, we have to continue developing our validation. We have to keep changing our tests. We have to keep upgrading things to keep up with the changes in the real world and the changes in your installed base. But one thing I can prove that there are no zero-day bugs in Linux kernel RCU. And the reason is that if I look at the bugs, the bugs maybe too, but the code that was there in 2005 that's still there in 2021, it's in 3 classes. There are preprocessor directives, which are trivially checkable. There are comments, which may cause confusion and thus bugs down the line, but they don't cause bugs right now. And there's blank lines. So no 0-day bugs, but that's no help. They're still bugs. With that, there's more information, as promised earlier, about the use of RCU and what it does and so on. I thank you for your time and attention, and I'm willing to take any questions you might have. Over to you.
Wow, that was a really a roller coaster ride, I would call it.
Thank you.
Taking us all the way in the history, Darwin. It was really cool. Thank you, Paul. Let's see what questions we have so far. The first question I would have for you was the reference back to let's have perf be cool again, right? So now, thank you for watching the panel from our last edition. Big kudos. But one of the reasons why we are complaining about not being cool is that actually there's less people coming in the space. Less people coming in the space and probably getting more complicated. Well, there's less people actually doing the good work. So I'm curious, what's your take? Do you think engineers want to learn about performance or actually do performance optimizations?
I think that it's a matter of trade-offs. Right now, the focus is on security. All right. But we've got a lot of places that have very large data centers and very large numbers of computers. Plus, things like smartphones are all over the place, and battery lifetime is a consideration. So there is, I believe, a pent-up demand growing for performance work. And should we ever get the security aspects more or less under control, I believe then performance will become more cool. And that's going to be both good and bad, as I said in the talk, right? But that'll encourage people to move in this direction. I mean, after all, you got a big data center, you have a megawatt here, a megawatt there. Pretty soon you're talking about real power, right?
Yeah. So it's really a Maslow pyramid kind of arrangement. Now we're still fighting at the base, trying to keep the barbarians away, and then we can worry about the megawatts. There is hope. Thank you for that. Second question I wanted to go over is the 10 million year bug. You're right. In a world with install base in the billions, that becomes not such a big defensive wall anymore. But talking about your current employer, they also say, you know what, we should move fast and break things. So is that the only way forward?
I think that what happens, I'll go back to your pyramid, okay? So I'm down here at the base of the pyramid. And if you take 3 things, you want productivity. I mean, you want code there fast. You want generality. If you do some code, you like a lot of people to use it so that you can amortize the cost of that code over a large user base. All right. And finally, you like it to go fast for all sorts of reasons. And by go fast, I mean energy efficiency. I mean raw speed, scalability, the whole works. Everything you can think of as being fast. All right. So here's a software stack. And the farther up you are on the software stack, the more specialized you tend to be. There are exceptions. Don't get me wrong. This is a very rough generalization. But at the very top of the stack, when I was at the top of the stack, I was writing for like a couple people. All right. And so what was important was productivity, because I couldn't spread my development cost over many people. I'm now at the bottom of the stack. What's really important is generality and performance. And so for example, for that security bug, that took me a full year to fix, right? That was a huge investment for something that was sort of defensive, kind of, right? But it was worth it because I was at the bottom of the stack. So move fast and break things becomes more the role at the top of the stack, where you need to keep up with trends and the requirements change more quickly and you don't have that many users. And moving fast and breaking things at the bottom of the stack is going to be somewhat slower and less prone to breakage if you're wise. So what software are you doing? You're going to have different pressures.
Wow, super deep answer. And for the people watching this, the motto has changed in the meantime. So now it's called move fast with stable infra. So that's really kind of supporting your point. Okay, let's see the next question. Going to Darwin, right? So natural selection, what we get is really bugs that were selected to survive our validation suite. Now, more and more companies have, there used to be a test function and a dev function, and a test function, there was a bit of a competition between the two. Now, devs in most places are supposed to write their own tests. So is there any hope? Do you think
So if I tell you that I'm the main author of both RCU and RCU Torture, are you going to be scared? It's true. And there's trade-offs. I've been in both environments. One of the problems you have with separate testing is it's really hard. The testers tend to be politically weak. A lot of them have ambitions to become developers, so they're scared to annoy the developers, and that means they're scared to really write nasty tests. The developers often, and this happens today too, that test isn't valid. No, it's not really a failure of my software. That test isn't valid. Why? Just get out of my face, right? And so I think it's one of these things where if we were living right, we'd be doing both. There are some tests that I have to write because I know what I'm trying to hammer on the software. On the other hand, I've met individuals. There was a kid who was an intern back in the 90s who was just really good at reading the code. He was interning for somebody else, not me. But he could read the code and he would write a test that would smack that piece of code really hard. So we called them sharks at that time, and there are people like that, and perhaps we need to make their work cool as well.
All right, so it's almost a question of talent, really, and then you're right.
And motivation.
Putting some of the responsibility with the engineers writing the code is probably the right thing to do, because I echo your comment on the tests being usually the politically weak party in that conversation. Yeah. All right, and kind of the last question I had was around your final claim: no 0 day bugs in RCU. But I think you're in a privileged position to be able to make that statement. I think most engineers probably won't be able to say the same, right?
Well, it's kind of a trivial statement. It's a stupid statement, a fun statement, but stupid. At least I've had fun with it. And the reason there's no 0 days bugs in RCU is every executable line of code in RCU has completely changed, is completely different from 2005 to 2021. There's nothing left from the old code. So there can't be any 0 day bugs because there's no 0 day code.
Oh, okay. All right.
So it's it's a claim. I don't know. It's one of these cocktail party claims. If I went to cocktail parties anyway. So since I don't go to cocktail parties, I inflicted on you guys.
Well, thank you. That elevates this conference to a cocktail conference. So I'm all for that. Paul, thank you so much for your time today and for the great talk. And looking forward to chat more with you in the panel conversation.
I'll be there. Looking forward to it.